Okay, I've started the recording. I would extremely sorry for this, but I think I would quickly uh, explain A once because it has to be a part of the recording for people who missed it. So we are starting it again. I'm extremely sorry for this. So let's start. So it says, so let's start with problem A. It says that initially you have a coin with value n. You can perform the following operation any number of times, possibly zero. What is the operation? The operation is transform one coin with value x, where x is greater than 3. So x is greater than 3 into two coins with value x by 4. And the question asks, what is the maximum number of coins you can have after performing this operation any number of times? Okay, so let me explain this question. Okay, so the question says that we are given an input, and the input for the problem is n. And the value of n is very large. The value of n can be anything from 1 till 118, right? So this is what the question says, that the value of n is very large. Now, since the value of n is 118, this immediately suggests us that any polynomial time solution such that a big O of n or even a root n solution would give TLE, right? So usually this would give TLE. So usually, the hint is that whenever you get such large constraints of n, the expected time complexity is log n. So for such large values of n, the expected time complexity is usually log n. So we need to actually think about a logarithmic solution. So why not first like understand what happens when we do the operations? So the question says that we are given an integer n, and in one operation we break it into two coins with value n by 4 each. So this is what the question says. Now, at every step, we can again break these coins, and we have to stop whenever the value becomes less than 3. And the question says, what is the maximum number of coins we can get? What is the max number of coins we can get? So this is what the question says. So let us run it for some case. Suppose I take n equals 250 and understand what happens. So if n is 250, in the first operation, n breaks apart into two values, right? So what is 250 by 4? 250 by 4 is 62, right? So if I perform one operation on 250, I basically get two coins with value 62 each. I hope that's clear. Now I can perform this operation on this 62 also because I need to maximize the number of coins. So let me perform the operation on 62 itself. So if I perform the operation on 62, I get the value of 62 by 4, which is 15. So I get 15 on these coins. Now I can again do an operation on these 15, and I will realize the value which I will get is 3. So I will get 3 here, right? Because 15 by 4 is 3. Now, just as soon as this happens, we cannot perform any operation on this because the value has become less than, because the value x is not greater than 3, right? When value of x is greater than 3, we can perform operation, otherwise we can't. So here we stop. Now there is one important observation in this problem. Look the number of coins in every level. Here the number of coins is 1, right? What happens here? Here the number of coins is 2. What happens here? Here the number of coins is 4. Since at every step a node breaks apart and produces two more coins, that means at every step the number of coins get doubled. So in this case, the number of coins become 8. So this is so that means at every step the number of coins increase by 2. And the beautiful part about this solution is that we can actually simulate it, because if I have a value of n, at every operation the value of n gets decreased by 4, right? So it becomes n till n by 4 here, then it becomes n till n by 4 square, then it becomes n by 4 cube. And what is the maximum value of n? N can be at max 10 to the power 18, right? And 10 to the power 18 is simply 2 to the power 60, which is 4 to the power 30. That means if I just simulate this entire thing, it will run only for less than equal to 30 operations, which will definitely pass the time limit. So actually, the time complexity of this solution is simply order log n to the base 4, which works pretty fine. So this is what the solution is. Let me just go through the code once. This is the code. K denotes the number of coins. Then we have taken n as input. If n is greater than 3, that means we can perform an operation. So at every operation, the value of k gets doubled. So number of coins get doubled, and the value of n decreases by 4. Whenever the value of n becomes less than equal to 3, that basically means that we cannot perform the operation even once more, and hence we break the while loop. So now the value of so it stops, and we can print k, which is actually the number of coins. So I hope it's clear. Uh, okay. Okay, great. So let me quickly start explaining problem B now. So here is the problem B. It says that Artem wrote the digit D on the board exactly n factorial times in a row. So he got the number D D D D D exactly n factorial times. Now he is curious about which odd digits from 1 to 9 divide the number written on the board. Okay. Uh, the values of n and d are given. D is some digit from 1 to 9, and n is some value which can be large. It can be up to 10 to the power 9. So let us explain. Let us understand what this problem says. Okay. So the problem says that in input we will be given two integers, n and d. So this is what we are given as input. N can be something very large. N can be of the order of 10 to the power 9, but d is some digit. It can be from 1 to 9. Note here that d can't be 0. D is something from 1 to 9, it can't be 0. Great. Now, the question says to construct a new number. Let me call that num. The question says to construct a new number num, which is basically d, 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 all the digits copied n factorial times. So observe that this is usually a huge number. Like for even like the value of n itself is huge. So n factorial is extremely large because n factorial is roughly n to the power n. So n factorial is extremely large, and this number num has this many digits into this. So this value num is very large. Like it has many digits. Just for the sake of some concreteness, like if I have n as say 3 and d is 2, then then what is my num? My num is simply 2 repeated 6 times. So this is 2 2 2 2 2 2. So realize how large this number gets even for some modest values of n and d. So now what does the question says? The question says that you look at all odd numbers. You look at all odd numbers. You look at 1, 3, 5, 7, and 9. And out of these, you print those odd numbers which are which are divisible, which are factors of num. So basically, you pick all those odd numbers I such that num modulo I is 0. This is the simple question. Now, this question would be extremely trivial if we could compute num, right? But obviously, we can't compute num. Even for some larger values of num, the number of digits in num would be extremely large that it would we cannot fit it even in a long variable. So we need to do something about this. So instead of actually computing num and doing the modulo operation, the idea was my initial idea was to have some divisibility checks. So, like, just for some example, let me show you. For one, say, let me take the case of one, right? For the case of 1, it is extremely trivial. All num modulo 1 will always be 0 because for any integer num, it is always divisible by 1, right? So that means 1 is also a part, 1 is always a part of the answer. So this is the part of the answer always, no checks required. So for 1, it's trivial, right? But what about 3? Okay, before 3, let me discuss this case 5. 5 is easier, right? Because a number is divisible by 5 only when its last digit is 0 or 5. But what is the last digit of this number? It's d, right? And d can never be 0. That is the part of the input. So d has to be 5. So if the number needs to be divisible by 5, you just basically need to check whether d divides by 5 or not. You do not need to explicitly construct this number. Just check for d and you will be done. So this is done. Even for 3, having such a check is easy. You just need to check whether n factorial into d, that is basically the sum of the digits of this number, right? There are d digits and there are n factorial digits and every digit is dumb, d. So the sum of the digits is n factorial into d, and you need to check whether this is divisible by 3 or not. But how will you check whether n factorial into d is divisible by 3 or not? Because n factorial is huge. You can't even compute this n factorial. That would lead to overflow issues. So here is a simple idea. So if n factorial into d has to be divisible by 3, either d has to be divisible by 3. If d is divisible by 3, you are done, right? If d is divisible by 3, then this product is divisible by 3. Or n has to be larger than equal to 3. Because think about what n factorial is. N factorial is simply 1 times, 2 times, 3 times, dot n, right? So if n is larger than equal to 3, then it would obviously have 3 as its factor. So you will be done. So if n is greater than equal to 3 or d is itself divisible by 3, then you are done. So having divisibility checks for 1, 3, and 5 are easy. I would believe me, divisibility checks for 9 is also easy. The problem comes with 7. For 7, devising such divisibility checks is not simple. You because like if you search on the internet, you would find divisibility checks for 7 which actually are recursive on the number of digits. And since the number of digits here is so large, you cannot actually use the divisibility check for 7. So because of this, I tried to modify my idea. So here is what I did. And interestingly, after I found out this technique for 7, I realized that I actually do not need to do all these divisibility checks for all digits separately. I can just use the same idea for all the digits and print the answer. So here is the idea. Suppose I need to check, suppose I is an odd integer. So I is some odd integer, say for example 7, it can be anything. And I need to check whether this number num, which is simply d, whether this is divisible by I or not. So what my initial solution, what I thought is, why not look at the remainders? So let me look at d modulo I. Let me also look at dd modulo I. And let me look at all these numbers. So I know d modulo I would be something. Say d modulo I is 3. Say dd modulo I, for example, is 2. Say triple d modulo I is 4. Say, now, suppose there are few things which can happen. Suppose d modulo I is 0. That means 4 times d modulo I is 0. So what does that mean? That means that at every multiple of 4, basically, this number becomes divisible by I. So I basically need to check whether n factorial, suppose this length, so here this length is k, the number of times after which the remainder becomes 0, that is k. So what I actually need to check is just whether n factorial is divisible by k or not, right? Because think about this. So here in this example, k is equal to 4. So what would happen after this? So 4 times d modulo I is 0. So what would happen when you do 5 times d modulo I? This thing will again repeat, right? After 0, you will again get a 3. Why so? Because what is 5 times d modulo I? This is nothing but 10 times 4 times d modulo I plus a d modulo I, right? And but we know that 4 times d modulo I is 0. So this entire thing vanishes to 0. That means 5 times d modulo I is simply d modulo I. So that means if you ever get a 0 here, things will start looping out. After 0, you will again get back a 3. So after this, you will again get 3, 2, 4, 4 and 0. 3, 2, 4, 0. So things will start looping out. So that means if you just need to check whether the final number, which is d n factorial times, that is if you just need to check that whether this number is divisible by I or not, you basically need to check that whether it comes in this integral multiple of 0 or not. So basically you just need to check that whether the n factorial is divisible by k or not. What is k? K is the number of steps after which you get a 0, after which you get the first 0. So I will just check n factorial is divisible by k or not. If I need to do that, I know that if n is greater than equal to k, it's surely divisible. Surely divisible. No checks required, because yeah, I said that n is simply 1 till n, right? And if n is larger than equal to k, n is the product of all these numbers. If n is larger than equal to k, then k would come somewhere in between, and then n factorial would be divisible by k. So this is correct. But if n is less than k, what you can actually do is you can compute n factorial. Why so? Because this value of k is not large. Think about this. This repetition of modulo, this value of k will never exceed I, right? This value of k would never exceed I. I will explain why this value of k is small. And since this value of k is small and n is less than k, you can actually compute n factorial and check this. So, okay, there is one more case when a 0 never comes. So, suppose you compute d modulo I and you get a value, say 2. And then you again say dd modulo I, you get a 5. And suppose you find dd modulo I and you get a 2 again. What does that mean? That means that things have started looping. After a 2, you got a 5, you got a 2, then you would again get a 5, right? And this thing will continue. That means you will never get a 0. You will never get a 0. So if you never get a 0, you know that this number num would never be divisible by I. So you do not need to print this anything. So, so the basic idea for this problem was, so here is the basic idea. You basically iterate over all the odd digits, say 1, 3, 5, 7, and 9. For 1, we know that the answer is trivial. It is always yes. So we can actually iterate over these odd digits. And whenever we are iterating over these odd digits, we can start computing the remainders. We compute the remainder for d modulo by I. Then we compute the remainder dd modulo I. And we keep on computing. Now, for all this, we will get some value, say 3, then a 6, then a 5. Whenever we see that the values have started repeating, suppose the value has started repeating. If a value has started repeating, that means we will never get a 0. So if we never get a 0, we can simply return, we know that, okay, this number will not, num would never be divisible by I. And if we get a 0 sometimes, we can just count the length. Okay, k is the length that it is, that after which we get a 0. So we will just check whether n factorial is divisible by k or not. And for checking n factorial divides by k or not, we can simply say that if n is greater than equal to k, yes, it's divisible. If n is less than k, why not compute n factorial? Because we then know that n is small. And then check whether n factorial is divisible by k or not. So let me show you the code for this. Here is the code. I first took n and d as input. And then here is the answer, which I will actually print. Answer, like I have pushed back 1 initially because I know that 1 will always be a part of the answer because any number is divisible by 1. After this, I iterate over the odd numbers. So I goes over the odd numbers. It starts from 3, increases by 2 at every step. So here is this r, and this r actually maintains the length after which I will get a 0, right? So here r maintains the length after which I get a 0, and num is the value. So num is basically this value d. So this is what num is. In the next loop of the iteration, this will num will become this. So at every step, I will first multiply num by 10, and then I will increase it by d. So that it basically appends one more digit d into the loop. So here I have done this. I have multiplied num with 10, I've added a d, and then I've simply increased the length by 1. And if I ever see that num divisible by I is 0, then this while loop basically breaks, because that means that, okay, I have got a 0. And if I do not get this, then this loop will break, and that would mean that f is false. That means I never got a 0. If I never got a 0, that simply means that I do not need to push back that value in the answer, because that will not be divisible, and I just continued. And if I get a 0, then r actually stores the length. So if I know that if n is greater than equal to r, I can push back that in my answer. If n is not greater than equal to r, I can actually compute the value of n factorial, which I have done in val, and then check whether val modulo r is 0 or not. Okay. So this was the solution for B. I hope it's clear.
Sir, can you please show the solution once again?
Okay, the code.
Yes.
Okay, here is it.
Excuse me, sir.
Yes, please.
Sir, can you please repeat the logic? Like, can you please explain?
Okay, let me do it for some values of n and d. So suppose let me take n as say suppose n as let me take n as 6, and let me take d as say 4. So here it is. So that means what is my number num? My number num is 4 repeated 6 factorial times, right? And
Yes.
what is 6 factorial? 6 factorial is 720. So it's huge. So we can't actually compute this number because there are 720 digits in it, which we cannot store in the long run. So we will now check for each odd digit whether num is divisible by I or not. So let's start. So first, we will not check for 1 because we know num is divisible by 1. It has to be for all digits. So I just push it in my answer array because I know it works. Uh, so let's start from the other digits. For all other digits, the condition is kind of similar. So let me start with 3 and show what happens. So I will actually try computing I will not try computing the values modulo 3. So first I start with 4, and then I compute 4 modulo 3. What 4 modulo 3 is? It's 1. Now I compute 44 modulo 3. What's 44 modulo 3? It's simply 2. Now I keep on continuing and compute 444 modulo 3. So 444 modulo 3, that would be, if you check, that would be again 2. Just a second, if I'm right. Okay, I think I'm wrong.
But it
So
should
that
be
would be,
0.
it should be 2, right? Okay, 441, that's divisible by 3, right? Okay, so this should be 2. So you have to realize one thing, that since things have restarted repeating once, it will keep on repeating. Like 4444 modulo 3, this would again be 2. And here, when you keep on concatenating 4, you will again always get the value of modulo 3 as 2 only. The value modulo 3 will never change. This is simply because if you have a 2, and then if you like if there is a 2, and then if you put a 4 behind, so that would be simply 2 into 10 plus 4 modulo 3, right? Okay, just a second. Yeah,
Sir,
2
it
into
should
10.
be 0 for the third one. For 444 modulo 3, it should be 0 and not 2.
Okay, I made a mistake. Just a second. Yes. Yeah, sorry. So it should be 0, right? Yeah, so
Yes.
444 modulo 3 is 0. So the idea is that if I get a 0 once, things will start repeating. So the next value has to be 1. And this value, 44444, this value will be 2 again. You can check it in a calculator. I actually do not have one, so that's creating some problems. So this will again be 0. So the idea is that once I get a 0, this remainder array would keep on repeating. And I know that this n factorial will come in some position, right? So my num would be when there, so this is the first element in this, there is just one digit, then there will be two digits, then there will be three digits. So similarly, I will get a number with n factorial digits, which will be my num. So I basically need to check num modulo 3 is 0 or 9, 0 or no, right? So I know that 0 comes at every third location. So 0 comes at the third location. Here 0 came at the sixth location. So I just need to check whether, so I know that a number will be divisible by 3. This number will be divisible by 3 only when it comes at a multiple of 3 in this position, right? So I just need to check whether n factorial is divisible by 3 or not in this case. That is what I need to do, because I know that a 0 comes at after every multiple of 3. So if I check that n factorial is divisible by 3, that means this number num will come at some multiple of 3 here. So its modulo 3 will be 0. But if n factorial is not divisible by 3, then this value num will come somewhere in between, and then the value will be either 1 or 2, and it would not be 0. So this is the basic idea, that if I get a 0 someday, then that means that the things will keep on looping. And then instead of checking num modulo 3 is 0 or not, I can just check whether n factorial is divisible by this length 3 or not. But obviously, checking whether n factorial is divisible by 3 or not is also not so simple, because n can be large, right? So the simple idea to do this is check whether n is greater than equal to 3 or not. If n is greater than equal to 3, then I know that n factorial is divisible by 3. So you can simply return yes. And if n is less than 3, then why not then I know n is small. Then why not compute this value n factorial? And then do the actual check n factorial modulo 3. So that is what I have done in the code. So here R was the length. If I know that n is greater than equal to R, that means n factorial is divisible by R. So I can just simply push it in the answer. But if I know that n is less than R, that means n is small. And in that case, I can simply compute the value of n factorial. So I just computed the value of n factorial, stored it in val, and then checked whether val is divisible by R or not. And I've pushed it in the answer and finally printed. Okay, so I hope it's clear.
Sir, I have a doubt.
Yeah,
Um,
sure.
so I just wanted to ask, like, is this a property of like the numbers over the having the same digits that, when we divide by a number, it just repeats, or it is in general for any number. If we just divide, it will just bound to repeat, like the
Uh,
pattern.
okay, so it is like, suppose you have a number, you have a number x, and so you have some value of x mod. Suppose we are playing with say 7. So you have a number x, you have some value x modulo 7, right?
Yeah, that right.
Yeah. So now if you concatenate something, suppose you added some digit d, what does the value? What does the new remainder becomes? It becomes 10x plus d modulo 7, right? So basically, the idea is like, if you suppose you try to compute the values of d modulo 7, dd modulo 7, and triple d modulo 7, and suppose it starts repeating here. So here it was 2, here it was 5, and here it was 2. So now when you compute 4 times d modulo 7, then what it should be? Don't you think that since triple d was actually divisible by 7, this thing actually does not contribute anything to the remainder? You can just throw away this. And if you throw away this, the value is actually d modulo 7, which is simply 2. So this is the reason why things will. Sorry, just a second. I did a mistake. Sorry. What I meant was let me show it for a 0. So d modulo 7 is 2. Just a second.
So I understood the part, like suppose it repeats for k, then how we will just go on with the further parts. But I couldn't understand that how, like you are selecting, like suppose you have just put the limit on r plus r is equals to I plus 1. So how
Okay.
we can say surety by surety that it will repeat only there, if it doesn't repeat then.
Okay, because you're getting remainders one by one, right? Like 5, 3, 1, 4. And suppose you get again a remainder 5. Okay. So suppose, so this was say d modulo something 7. So this is 2 times d, 3 times d, 4 times d, and this is 5 times d modulo 7. Okay. So let us compute what 6 times d modulo 7 is. That would be best. Like let's not think that okay it will repeat, and let's compute what 6 times d modulo 7 is, right? So what is 6 times d modulo 7? So think about this. 6 times d modulo 7 can be thought of 5 times d modulo 7 into 10 modulo 7 plus d modulo 7, right? Now, what is 5 times d into 10 modulo 7? We know 5 times d modulo 7 is 5. So here this is 5 times d modulo 7 is 5. Okay, so this is okay. Just let me take a solid example so that would be clear. Let me take 2. So what is 2 modulo 7? 2 modulo 7 is 2, right? What is 22 modulo 7? It's 1. What is 222 modulo 7? It is simply so it is simply 12 modulo 7, which is 5. What is then 2 to 2 modulo 7? That would be uh, 52 modulo 7. That should be 3, right? If I'm wrong with numbers, then someone please just tell me. If it's 2 to 2 modulo 7, that would be 4. Now, if I have 6 times 2 modulo 7, that would be 0. Now, what would be 7 times 2 modulo 7? What would be this? What do you think? My argument was these things need to repeat, so it should be 2. But why? Let me show you. Like if you try to compute this, what this thing modulo 7 is, then you can actually write this thing as 2 to 2, then again 2 to 2, 0, modulo 7 plus 2 modulo 7, right? Now this thing was divisible by 7. So this thing, if you concatenate a 0 again, this remains 0 divisible by 7. So this thing actually vanishes out. So this is 0. And 2 modulo 7 is 2 itself. So just because this part is 0, actually this part vanishes out from the remainder and this thing remains, which is same as this. And that is the reason this value again copies out here. And that is the reason why you get a 2. So that is the basic reason why things need to repeat. So if you ever say, so after a lot of distinct values, so you can at max get 7 distinct values. After 7 distinct values, either things will start repeating or you will get a 0. One of these two things have to happen, which actually explain why I've added this check r greater than equal to I plus 1. Because I know that if r is greater than equal to I plus 1, that means things must have started repeating and I've still not got a 0. Okay, now let's start with problem C of the contest. So here it is. It says that you are given an array A of n integers where all integers except for at most 1 are equal to -1 or 1. The remaining element x satisfies minus 10 to the 9 is less than equal to x, which is less than equal to 10 to the 9. Now the question says that find all possible sums of subarrays of A, including the empty subarray, whose sum is defined as 0. In other words, find all integers x such that the array A has at least one subarray, possibly empty with sum equal to x. A subarray is a contiguous subsegment of an array. Output these sums in ascending order. Each sum should be printed only once, even if it is achieved by multiple subarrays. Okay, the number of test cases is 10 to the 4. The value of n is 2 times 10 to the 5. And the sum of n over all test cases does not exceed 2 into 10 to the 5. Okay, so let me quickly explain the problem once. So the problem says that we are given an array A. We are given an array A, which are basically integers, which are all 1 or -1. And there may be one value which may be exceptional. So here there is one value which is not neither 1 nor -1. And it is not guaranteed that such a value would be present. But if such a value not equal to 1 or -1 is present, then that would be at most 1. So this is what the question says. Now, the question says to print all possible subarray sums. So what is a subarray? A subarray is just a contiguous segment L to R from the array. So any contiguous segment L to R from the array is a subarray. So for example, this is a subarray. And what is the sum of this subarray? The sum of this subarray is 1 plus 1 minus 1, which is 1. So the question asks that we have to print all possible distinct subarrays which are possible. So let me take a quick example. So let me take this. Let me take a smaller example, say minus 1 and 2. So if you look at this array, minus 1 and 2, what are the possible subarrays possible? So first of all, the question says that you can include the empty subarray. So the empty subarray has a sum of 0, so you include 0. Then minus 1, this is itself a subarray, a singleton set. So minus 1 is a possible sum. 2 is also a possible sum. You just take this element. So 2 is also a possible sum. And this entire subarray together, that is also a possible sum, which has a sum of 1. So here there are 4 distinct possible sums. Now the problem is, why can't we just brute force? The problem is that there are n square subarrays in an array. There are n square subarrays in an array. So that means there could be n square different sums, right? So if there are n square different sums, then that would give TLE, right? Because the value of n is order like of the order of 10 to the power 5. So that means you can't run a big O of n square code. That would give TLE. Since n is 10 to the power 5, the expected time complexity of the solution is order n. Okay, so that means we have to meet something like a linear or a log linear solution, like an order n or an order n log n solution for this. Now, when I started solving this problem, I thought, let's forget about this extra element which I have. So here I know that there can be one exceptional element which is 1 or minus 1. So I thought, let's not think about this. Let's think about arrays which are only 1 or minus 1 made. So here there is a special case. So think about arrays which have either 1 or minus 1. So all elements are 1 or minus 1. So what would be the possible answer? So let me take just an array for simplicity. So suppose I have minus 1, 1, minus 1, and a minus 1. So let us compute what are the possible subarray sums here. Look at this, that minus 2 is possible. So here this is minus 2. A minus 1 is possible, you just take one element. 0 is possible, that's the empty array. 1 is possible, right? You just take a single element. Anything else? Probably anything else is not possible in this. So I realized that anything in the answer minus 2 to 2 is possible. Then there is one more example given here. That is 5 minus 1s just plugged together. And you can see that any sum from minus 5 to 0 is possible. So that actually I developed an intuition that there is some contiguous segment of values which are possible. So for this subarray, there is a contiguous set of values from minus to 2 such that everything in between is possible. Even for the array when there are 5 minus 1s, you can see when there are 5 minus 1s, anything between minus 5 to 0 is possible. So this was the basic idea. So I thought that there is some range of values such that all values inside that range are possible and anything outside this range is not possible. Now, this was the intuition behind the problem. So, what is the basic formal argument for this problem? The argument is, suppose I compute all the subarray sums in such an array. So I have an array where all the elements are 1 or minus 1, and I basically compute the maximum subarray sum here. I will later show how can we compute this. But suppose the maximum subarray sum is mx and the minimum subarray sum is mn. So my claim is that all values between mn and mx are possible. For example, here the maximum subarray sum is 0. You just take the entire empty subarray, and the minimum subarray sum is minus 5 because you take all the elements and then you get a sum of minus 5. So here mn is minus 5 and mx is 0. Similarly, in this case, you can look that the maximum possible subarray sum here was 1. You just take a single element. 0 is possible, that's the empty array. 1 is possible, that's the and the minimum sum was -2. You just take these two elements. So anything from -2 to 1 was possible here. So my argument is that whenever you have an array which is completely made up of ones and minus ones, then and suppose the minimum subarray sum is mn and the maximum subarray sum is mx, then all values in the range mn to mx would be possible. Why so? Because suppose I have an array A. Suppose I have an array A, and then I have these suppose it has some values, all values are -1 to 1. I do not care much about the values, but suppose I have this segment LR. This is L to R where the maximum value is stored. And suppose this is one more segment L1R1 which has the minimum value Mn. Now you have to realize this, that when I shift the subarray from L to L1, and when I shift the subarray from R to R1, at every step the value of the sum either decreases by 1 or increases by 1, right? Because every element in the array is either 1 or -1. So it is either 1 or it is -1. So if I increase this value, the value of this subarray sum mx will either decrease by 1 or increase by 1. So suppose the subarray sum is here mx, and suppose I have to and I will move these pointers L and R, and I will make it to come to mn. But when I will change this mx and make it to mn, at every step it cannot jump by more than 1. So at every step it has to it can go up, it can go down, but it has to always change by 1. Now whenever it will always change by just 1, basically to reach from mx to mn by just having making jumps of size 1, you have to touch all the elements in the array, right? So you have to touch all elements in between mx to mn. So that is the idea why. So that is the argument why if all the elements are 1 or -1, then all the values between mn and mx are possible. Now I will actually not show. There is a very standard algorithm which is known as cadence algorithm, cadence algo, which actually helps to find the maximum subarray sum in order n time. So you give any array and you can find the maximum subarray sum in order n time. You would have probably read this in theory or will read it sooner in classes. But this is an algorithm which in order n time will help you find the maximum subarray sum. And if you know if you know an algorithm which can find the maximum subarray sum, then what you can do is you can also find minimum subarray sum in the same time. You can also find minimum subarray sum in order n time by just invoking this algorithm on an array where all the values are negative. So that is basically, suppose I have some array A1 -1 something, and suppose I know how to find maximum subarray sum using cadence algorithm, and suppose the maximum subarray sum is 5. You can also find the minimum subarray sum. How so? You just basically construct the minus A array. So basically you flip all the elements. You change 1 to -1 and -1 to 1 and invoke cadence algorithm on it. So you get maximum subarray sum, which is 2. So you know the maximum subarray sum on this minus A array is 2. That means the minimum subarray sum of A array should be -2. So using this, invoking just the cadence algorithm, you can compute the maximum value and the minimum value. And this would actually help you to reach a solution that whenever the array is always constructed of -1s and 1s, then you can simply invoke the cadence algorithm and find the solution. Uh, now, Now let us come to a case when there is one extra exceptional element which is neither -1 nor 1. Okay, so let us take this test case 1, -1, 10, 1 and 1, and let's see what happens. So here is this test case 1, -1, 10, 1 and 1. So now look at this. This is a subarray and this is a subarray. Both of these are arrays which are constructed of only ones and minuses. This is also an array which is constructed of only ones and minuses. So you could first invoke cadence algorithms separately on these two arrays, and suppose you get some mn1 to mx1 here. So you know all values between mn1 and mx1 are possible. Also, all values between mn2 and mx2 are possible. So all subarrays which are completely included in this region or completely included in this region are already covered. For example, here the value of mn1 will come -1 and the value of mx1 will come 0, right? Because the smallest possible subarray sum is -1, the largest is 0. Similarly, here the value of mn2 will come 0 because you have to take the empty subarray and max is 2. So that is done. These two ranges are clear and all values in these two ranges are possible. Now we need to think about those subarrays. We just need to think about those subarrays where the 10 element is included because this is the exceptional element. So what I thought, let's think about all those subarrays which contain 10. All those subarrays which contain 10, basically, suppose this is the entire array. So suppose this is the entire array A. So all those subarrays, and suppose this is a subarray we are interested in from L to R. So all those subarrays which contain 10 basically contain a prefix of the right hand side. So this is the right hand side of the array and this is the left hand side of the array beyond 10. So it contains some prefix from this part and some suffix from this part, right? So my idea was why not compute the minimum possible suffix sum and the minimum possible prefix sum and the maximum of those. Suppose the minimum possible suffix sum here is mns and the maximum possible sum is mxs. Similarly, the minimum possible prefix sum here is mnp and the maximum possible prefix sum is mxp. So, and suppose this value is v. Then don't you think that any subarray sum, the minimum which I can have will we take the minimum from here, that would be mns, take the minimum from here, that would be mnp, and simply add v because you have to do it always. Similarly, the max you can have is simply take the max from both sides, mxs plus mxp, and then you v, and then you take v, and you know that all subarrays which include v has to be will get values in these two range only. For example, for a concrete example, let's take this 1 -1 10 1 and 1. So here it is 1 -1 10 1 and 1. So let us take all prefixes of this part. So what is the prefixes of this part we can get? We can get a 0 if we take a prefix of length 0. We can get a 1 if we take a prefix of length 1. And we get a 2 if we take a prefix of length 2. Similarly, here I can get a, let me take all the suffix sums. I get a 0 if I take a suffix of length 0. I get a -1 if I get a suffix of length 1. And then I again get a 0 if I take a suffix of length 2. So that means from here, the minimum I can get is -1. The minimum here I can get is 0. So that means what is the total minimum I can get? 10 here, because I have to include this element. -1 from here and a 0 from here, right? So that will give me a value of 9. And what is the maximum I can get? That is 10 again. I have to include this. 0 from here, I will take the maximum from here. And 2 from here, I will take the maximum from this side. So the value I can get is 12. That means if I include 10, the range of values which are possible is from 9 to 12. So that means there are three ranges which we need to consider. Whenever I get an exceptional element, I need to consider three ranges. First, let me forget about this 10. Let me solve the problem only for the left part. I get some range -1 to 0, which can be found from cadence algorithm. Similarly, forget about this 10, solve the right part. You again get a range 0 to 2 from cadence algorithm. So here are the two ranges which you get independently by solving the left and rightmost parts of the problem. So that is -1 0 and a 0 2. And then solve the part when you have to include v. So when you have to include v, just find the minimum suffix sums and prefix sums and same the maximum, and then you will get a range. So you get a range 9 and 12. So the final answer, where you have to print all the distinct values, would be basically the union of all these things. So any number in the range -1 to 0, then 0 to 2, and then 9 to 12. So you can also look at the solution. Basically, it has printed all the numbers from -1 to 0, from 0 to 2, and then from 9 to 12. So this is the idea. Let me get you through the code once. So this is the code. Frankly, I have picked during the contest. I picked this code from GFG. You can look at it. You can just simply search cadence algorithm, and you will get a function. And this is just a function order n implementation where it takes an array and simply returns the maximum possible subarray. After this, I have this implementation. Actually, I wrote this in a hurry during the contest, so the implementation is not clean. Clean, I understand. Uh, but I will tell you what the idea is. So the idea is very simple that I first take all these elements. VV is the element which is the exceptional element, which is not 1 and not -1. And II is simply the position of the element. I initialize II with -1. So if II is not -1, that basically means that there is some exceptional element in the array. So for that, first I simply compute the prefix and the suffix sums. I stored it in a set and found out the minimum and the maximum elements. It was actually a set was not at all required here. You could just maintain two variables. Apart from that, I constructed the positive and the negative arrays because I told you that I need to invoke the cadence algorithm, and I computed these two ranges from A2 B2 and A3 B3. So these are basically the construction of these two ranges. This is how these two ranges are constructed: mn1 mx1 and mn2 mx2. So this is it. Uh, apart from that, I have also constructed the arrays separately v1, v2, v3, and v4. So these are basically separate construction of these elements. So I have constructed these vectors separately because I have to invoke cadence algorithm and pass it to find separately the answer for them. And after this, after taking the union of everything, just I've got three ranges: A1 to B1, A2 to B2, A3 to B3, and I've just pushed them in my set answer. I've also included zero because an empty set has to be always considered, and then I've just printed my set. Similarly, this was the if part when II is not -1. That means there exists one exceptional element. If there is no exceptional element, what you can do is you can simply just take the maximum subarray sum. Then you can compute the negative of the array, and then you can find the minimum subarray sum by the idea I told you. And then I just printed everything from B to A. That's it. The code may not be very clean, but the idea which I discussed is implemented basically.
So,
Okay.
what if we don't get minimum there? Like for example, what you are showing.
Yes. Continue.
So, can you please show that example? Yeah.
Yeah.
So, what if the indices of 1 and -1 are reversed, like swapped? Like our array is -1, 1, 10, and 1, 1.
Okay. Okay.
Right?
So the idea remains same. So if my array is -1, 1, 10, and 1, 1. First, you invoke the algorithm, cadence algorithm separately on these two arrays. These parts will be done, right?
Yeah.
So this will give you a range again -1 to 0, and a range 0 to 2 here. So these are the ranges which are not changed. So let me
So, but
consider this.
the subarray we'll get here from this example is 10 and 0 will not get -1, right? Because that wouldn't be a subarray.
Yeah, exactly. Like if I compute the suffix sums here, then the suffix sums I will get is 0 when I take no suffix, then 1 if I take a single element, and then a 0 again. Similarly, if I find the compute prefix sums here, I will get 0 for a prefix of length 0, then 1, and then a 2 here. So now if I take the minimum, so what is the minimum element you can get? The minimum element you can get including 10 is simply 10 plus the minimum from this side, which is 0, plus the minimum from this side, which is 0. So that is 10. And the maximum you can get is 10 plus the maximum from this side, which is 1, plus the maximum from this side, which is 2, which is 13. So that means your answer will change because now you will not print, you will print -1, 0, 0 to 2. That's all right because that's independent working of the remaining part of the code. And apart from 9 to 12, now you will get 10 to 13. And you can actually check that you will get no subarray in this array with a sum of 9, right?
Yeah. Okay.
Okay, I hope it's clear now.
Yes. Yes.
Okay. Yeah, sure. For special parts, you can also calculate using an order in loop. Probably a better implementation could have been done. I have basically did some multiple iterations, but as long as the time complexity doesn't increase much, it's fine because that would anyway pass the time limits. Okay, so let me discuss problem D now. So it says that given three integers L, R, and G, find two integers A and B such that their greatest common divisor GCD equals G and the distance A minus B is maximized. If there are multiple such pairs, choose the one where A is minimized. If no such pairs exist, output minus 1 and 1. Okay. There are 1000 test cases which will be given. At every test case, we will be given three values L, R, and G, such that L and R lies between 1 to 10 to the power 18, and G will be given, which again lies between 1 to 10 to the power 18. So let me quickly explain the problem. So the input which will be given is three values. A range L and R will be given, and a number G will be given. And we need to output two numbers A and B in this range such that the GCD of A and B is G, right? So the GCD of A and B is G. And apart from that, we also need to include that we have to also maintain the condition that A and B are far apart. So the distance between A and B, or we can say the absolute value of A and B is as large as possible. So we have to also ensure this. And the question is said that if you get multiple such values where this is large and this is same, then you print the one with the smallest value. Okay. Now, frankly telling, I have written a solution and it worked, but it was completely based on intuitions today, and I really do not know the formal proof behind it. So I will explain the intuitions, what led me to think such a solution, and then if anyone can ever if anyone knows the formal solution, then you can tell me like why does it formally works. So first of all, I want two numbers in the range L to R such that their GCD is G, right? Now, if two numbers A and B have their GCD is G, then that simply means that G divides A and G divides B, right? Because G is a common factor of both A and B. So if the GCD is G, that means G must be a factor of both A and B. So first of all, I thought why not scale this problem down? So I thought let's scale this problem down to the seal value of L by G and R by G, floor value. Once I do this, now this is my new range, and I need to find new A and B such that A and B are co-prime, right? So this is something like suppose you have to find two numbers with a GCD of 6 in the range 5 to 20. So I know that two numbers with a GCD in the range 5 to 20, two numbers in the GCD with a GCD of 6 can be 12 and 18. So, but my idea is why not scale it down to a smaller value? Like why I know 12 is nothing but 6 times 2, and 18 is nothing but 6 times 3. And if I want the GCD of these two values to be 6, so that basically means that when I divide them by 6, the remaining numbers which I get 2 and 3, they must be co-prime, right? They cannot have a common factor. Because they have a common factor even after dividing by G, then that common factor would also contribute to the GCD, and the value GCD would not remain G, right? So I just basically scale this problem down. So if I had a range 5 to 20, I basically converted it to a range 1 to 3. 1 to 3. I basically divided 20. I divided 20 by 3, and I take the floor value because I have to take smaller values than this. And I converted 5, and I divided 5 by 6, and I took the seal value because I need a range smaller than that, right? And here I have to find two values which are basically say 2 and 3 such that they're co-prime. Because if you get two values 2 and 3 which are co-prime, you can just multiply them with 6 and get the original values back. So that was my initial idea. So that I will scale the problem down and solve the problem. So now the equivalent problem is that I have a range L to R and I have to find two integers L and R. I have to find two integers A and B in this range such that A and B are coprime. So that was my idea. Now I thought that okay, why not fix A? Why not fix A and then think what values of B I can get. So suppose I fix some A and then I have to find a value of B. I have to find a value of B such that GCD of A and B is 1, right? I have to find two coprime integers A and B. And I have to take B as large as possible. I have to take B as large as possible because that then only the distance will be maximized. So my idea was that if I try to run this code, I just try to check which values of B are possible. Then probably I will not get a very large range. If I write a simple brute force code, like suppose I fixed an A, and then I just iterate over all B's from say R because I need to take a large value. So let me iterate from R and let me iterate over some values and just check that whether GCD of A and B are 1 or not. So my idea is very quickly in very few iterations, this loop will break. This was the idea because if you fix a number X, then you can't get a very large range such that no one is coprime. Like suppose I have fixed a number X. I have fixed a number X, and suppose I start iterating from B from this larger range. So I start looking at these numbers. Okay, just a second. Yeah, so I start looking at the numbers R, R minus 1, R minus 2, and so on. So the idea is very quickly, in very few number of iterations, I will get a value which will be coprime with X. Because think about this, that if I do not get a number, quickly a value which is coprime with this, then that means for R minus 1, R minus 2, everyone has a prime factor with X, right? So that means suppose X has a prime factor 3. So 3 cuts all these numbers because so 3 cuts all numbers with a distance of 3, right? So similarly, if it is a prime factor 7, so that cuts all numbers with a distance of 7. So in order to, if you need to cut actually all the numbers so that they are not co-prime with X, that means that would need a lot of prime factors. But a number X can't have many prime factors, right? So my simple intuitive idea was that probably that if I let this code run for few number of iterations, I should get a solution. I should get the optimal solution. Probably the range which we are looking for would not be very large. This was an intuitive idea, and I did not have any formal argument to do this. I just thought of coding it up in the solution during the contest, and luckily it worked. So here you can look what I have done. I have just scaled down this problem. So I have taken L, R, and G as input. I have scaled down the argument to L1 and R1. So R1 is simply R by G, and L1 is seal value of L by G. So this, if you do not know this, then this is actually a way of doing seal instead of using the seal function. So whenever you need to compute A by B, the seal value, you can just find the floor value of A plus B minus 1 by B. This relation usually comes handy because doing floor in programming languages, at least in C++, is easier, and it can be done using only the division operator. So I've just taken L1, which is the seal value of L by G, and R1, which is the floor value of R by G. This condition you can ignore. This I wrote during the contest. But here the idea is very simple. Here I have just ran the code for 200 iterations. You can look, just I have ran from L1 to min of L1 plus 200. So I've just let the code ran for 200 iterations because of an intuitive idea that probably if I let it run for 200 iterations, I would get a value which would not be coprime. So I have let it run from L1 to L1 plus 200. For every value of I have just computed a value. I have just checked what is the largest possible value of j such that it is coprime. And whenever I get a larger distance, I've updated it. And after this, if I have found a value in this range, then I have again scaled up the integers ii and jj and multiply them with g to get the answer. And if I have not found it, I have ran it with -1 minus. Though I do not know a formal proof for this, but usually in number theory, intuition matters, and lot of times you can actually solve the problems by looking and understanding it. So I hope it's clear. Okay. If there are any doubts, you all can ask me. Okay, great.